At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like the video, you'll love my book. Learn more about it at rescueedu.com or hear more about it at the end of the video. The second semester book comes out in fall 2020. Let's talk about VSEPR theory and how to correctly draw organic molecules in 3 dimensions. First, let's review the basic concepts of VSEPR theory. VSEPR stands for valence shell electron pair repulsion. It's a very simple way to accurately predict the geometry of groups around an atom in a molecule. It's based on the fact that groups of electrons around an atom repel each other. Electrons are negatively charged and want to be as far apart from each other as possible. If you identify how many groups of electrons there are around an atom, you will know its geometry. A group of electrons can be in a single, double, or triple bond. It can also be a pair of non-bonding electrons. In organic chemistry, we only need to know about tetrahedral, trigonal planar, and linear geometries. First, we'll talk about tetrahedral geometry. An atom with 4 groups of electrons will have a tetrahedral arrangement. Geometrically, 4 groups are always farthest apart from a central point when they are in a tetrahedron. This arrangement minimizes electron repulsion. Methane has 4 identical CH single bonds. It is not flat, and it does not have 90-degree bond angles, as its Lewis structure suggests. Experimentally, it is known to be tetrahedral, with exactly 109.5-degree angles. This puts the electrons in the CH bonds as far apart from each other as possible. It's essential to be able to draw a correct tetrahedral geometry. Here are the steps. Step 1. Draw 2 bonds in the plane of the paper approximately 109 degrees apart. I usually draw them to the left as shown. Step 2. Exactly opposite to these 2 bonds, draw the other 2 bonds. In this case, that means draw them down and to the right. Draw 1 bond forward out of the plane of the paper, which is indicated by making it a bold triangular line. Draw the other bond in back of the plane of the paper. This is indicated by making it a hatched triangular line. They are meant to be right on top of each other, but we need to slightly skew them so you can see the back hydrogen. There are many ways to draw this tetrahedral geometry. I usually stick to this first way or this second one to be consistent and avoid confusion. But these 2 drawings are perfectly fine. Just make sure to draw a very clear tetrahedral geometry, whichever one you pick. There are many incorrect ways to draw this geometry. The first and second representations are common, but they have 90-degree bond angles, so they can't be right. The last molecule has several things wrong. It has many bad bond angles. It has this 45-degree angle here and a 180-degree angle here. Also, the hatched and bold lines are not next to each other. If you were to build models of any of these incorrect representations, you would see they are not tetrahedral. I recommend you stick to our method for drawing tetrahedral atoms. Ammonia has 4 groups of electrons in 3 single nitrogen-hydrogen bonds and a non-bonding lone pair. We say it has tetrahedral-based geometry. Experimentally, you actually see a trigonal pyramidal arrangement of atoms because the lone pair is invisible. The bond angles are 107 degrees instead of 109.5 degrees. The non-bonding electron pair resides closer to the nitrogen because it's not pulled away by bonding to a hydrogen. The lone pair acts bigger than the bonding electrons and squishes the NH bonds together. All nitrogens in organic molecules with 3 bonds and 1 lone pair are also tetrahedral based, but appear to be trigonal pyramidal. Water also has 4 groups of electrons and 2 single OH bonds and 2 lone pairs. It's also a tetrahedral based geometry. Experimentally, you see a bent, sometimes called an angular geometry. The bond angle is 105 degrees, which is even smaller than the 107 degree bond angles in ammonia. That's because there are now 2 big non-bonding lone pairs squishing together the 2 OH bonds even more. All oxygens in organic molecules with this bonding pattern are tetrahedral based, but appear to be bent. Next, let's look at trigonal planar and linear geometries. 3 groups of electrons around a central atom are farthest apart when they are trigonal planar. The bond angles are 120 degrees. The central atom and the 3 groups are planar. Again, this geometry minimizes electron repulsion. Methyl carbocation is the simplest organic molecule with this geometry. It is entirely flat, so it can accurately be drawn in the plane of the paper. Sometimes a side-on view is better. In this view, one of the hydrogens is also in the plane of the paper, one is forward, and one is back. Boron trifluoride is another common example of a trigonal planar molecule. Ethylene is a classic organic chemistry example of trigonal planar geometry. Each carbon has 3 groups of electrons, 2 CH bonds and 1 CC double bond. The entire molecule is flat. We'll discuss why it's flat in the hybridization section, topic 1.4, which is next. The bond angles are not exactly 120 degrees because the attached groups are not all identical. You can accurately draw the molecule entirely in the plane of the paper or in a side-on view. Both of these representations are important to know. 2 groups of electrons around a central atom are furthest apart when they have linear geometry. The bond angle is 180 degrees. Carbon dioxide with 2 carbon-oxygen double bonds is linear. Acetylene is the simplest organic molecule with this geometry. The 2 groups of electrons come from 1 CC triple bond and 1 CH bond. All 4 atoms are linear, and both bond angles are 180 degrees. It is always drawn in the plane of the paper. Next, we'll have a quick introduction to three-dimensional drawing in organic chemistry. A single tetrahedral carbon in a molecule such as trichloromethane can be drawn many ways in 3 dimensions. Notice that in the last drawing, we can leave off specifying the carbon, so this is a bond line drawing. Ethane has 2 carbons, and there are several ways to draw it in 3 dimensions. The carbon-carbon bond is drawn horizontally, and the attached hydrogens are arranged in a clear tetrahedral arrangement at each carbon. Not all of these representations are identical. In B, the hydrogens are all lined up, but in A, they are not. A and C are identical to each other, but just flipped over. A and B, or B and C, differ by rotation around the central carbon-carbon bond. These subtly different rotations are called conformations and will be studied in topic 4.1. A very common mistake is to draw 4 atoms in a linear arrangement and then add on the other hydrogens forward and back. Both of these have 180-degree bond angles, which is incorrect. Each carbon should be clearly tetrahedral, and all bond angles should be fairly close to the perfect 109.5. Long chain linear molecules are drawn as zigzags. The end hydrogens are included in the zigzag. The other hydrogens point forward and back at each carbon. If you put substituents on the chain, you can draw them forward, back, or as part of the long chain. You can simplify by leaving off the hydrogens on the substituent carbons and just show the position of the substituents. Double bonds are flat. They can be drawn in 3 dimensions either in the plane of the paper or side-on. In the side-on representation, the back atoms are actually behind the front ones. The molecule is skewed slightly to show the back atoms. It is important to know both of these representations. 2 substituents on a double bond are trans if they are on opposite sides, and they are cis if they are on the same side. Cis and trans isomers are different molecules and have different properties. Cyclic molecules can be drawn in several different ways to convey 3-dimensional information. We can draw the ring carbons in the plane of the paper and have substituents coming forward or back. We can also draw the ring using a Haworth projection. The flat ring is drawn side on and the substituents point up or down. In cyclic compounds, 2 groups are cis if they are on the same side, that is, the same face of the ring. Here we have them both pointing forward, but they could also both be pointing back. Notice that we can leave the hydrogens off the substituent carbons to simplify the drawing. In the Haworth projection, we have them pointing up, but they could just as well be pointing down. You must always draw the hydrogens on the carbon a substituent is attached to in a Haworth projection. If 2 substituents are trans, then they are on opposite sides, that is, opposite faces of the ring. In actual fact, most rings are not flat but are puckered. Neither of these representations is an entirely accurate 3-dimensional representation. We will discuss how to very accurately draw rings in 3 dimensions in topics 4.2, 4.3, and 4.4. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. The book is organized into standalone topics so you can quickly teach yourself a few troublesome topics. It's also logical and organized from beginning to end, so you can easily learn the whole semester if you need to. My self-help book is particularly valuable in difficult learning situations, but you can also use it to get an edge. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.